Analyses of stimuli. Visual stimuli. Observations of the social interactions of these pagurids led me to consider certain movements and positions as possible elements of the communication systems of these crabs. But observations of interactions alone, however consistent as to sequence, cannot establish the stimulus value of any physical cue. A number of experiments were carried out in an attempt to prove that the observed physical changes are effective stimuli in the behavior of these crabs. The behaviors which were observed most extensively were, of course, visual movements and postures, since these are the easiest for a human observer to sense. Certain movements and positions of the chelipeds and ambulatory legs were described in earlier sections. In order to test the hypothesis that these postures are indeed visual stimuli, series of model presentations were carried out with a number of the species studied. Following initial failure with artificial legs, experiments incorporating models fashioned from the exoskeletons of individuals of the species being tested were carried out. The test and control models were obtained by choosing several approximately equal medium-sized individuals of the species, killing them, and placing the cephalothorax and attached appendages in the desired positions to dry. Normally molted exoskeletons were used for some models in Clibinarius, cubanensis, and Pagoristes grayi. The chelipeds and ambulatory legs were held in either neutral, normal walking, etc., or test, aggressive display, positions by bits of clay and or cork. After 24 hours, the specimens had dried and their limbs were relatively fixed in position. The entire cephalothorax was then glued to the end of a glass rod 10 centimeters long, 4 millimeters in diameter. Glue was also placed around the proximal joints of the appendages to add rigidity and maintain limb position. After an additional 24 hours, the models were ready for use except in those cases where alteration of the normal color pattern was carried out. In each case, the test model was an exoskeleton, the limbs of which were arranged in the raised or extended position of an aggressive display. The control model was an exoskeleton of the same size whose limbs were in a neutral position. In the case of Calcinus tibicen and Clibinarius tricolor, tests were carried out to measure any possible stimulus value of the white tips of their chelipeds and ambulatories. For this, additional aggressive models with the white tips of their limbs colored the same color as the rest of the limb were used, and the reactions compared with those shown to normally colored aggressive models. Test and control models for each display were presented individually to 50 crabs in each species. The sequence of test-control presentation was constantly varied. Every individual was tested only once with each stimulus control set of models. The individual to be tested was placed in the test container, and, after the crab had adjusted to the container sufficiently to be moving about, the models were presented to it one at a time. Each model was moved in front of the organism being tested to within a distance approximately equal to the total length of an individual of that species. The distance of model presentation varied from species to species, but was held constant for each species. Every effort was made to present the test and control model in an equal manner. The movement of presentation was slow and even in all cases, such that it was judged that the crabs were reacting to the position of the model's appendages and not its overall movement. The model was held quietly in front of the test animal for 3 seconds and then removed. The reactions of the individuals to the models were recorded. These reactions are listed in tables 7 and 8. 2 by 2 contingency tests were calculated to see if the reaction classes aggression, aggression with retreat, and retreat are statistically of the same population of reactions. In all but 2 cases, this was true, i.e., all active reactions shown to the models could be regarded as one set. The reactions shown to the test and control models were then compared with the nothing, no reaction class, using chi-square tests. In addition to these static model tests, one series of presentations was carried out with a model in which motion of the limbs could be controlled by the experimenter. In this experiment, 2 wooden and glass apparatus were fashioned in which a major cheliped from a specimen of Calcinus tibicen could be placed and moved upward in an approximation of the motion of a cheliped extension display. Control and test models with motion were presented to 50 Calcinus tibicen. There was no statistical difference between the behavior patterns shown toward the cheliped extension with motion and those shown toward the test model in the static series. As can be seen from the results of the model presentations, the position of the appendages can act as stimuli, sensu stricto, in the aggressive behavior of these species. On the basis of the contingency tests, almost all reaction classes were lumped and tested against the nothing class for each display. This was not done for the tests of the ambulatory rays in Pagurus bonarensis and Calcinus tibicen, since the crabs had shown a considerable amount of aggression toward the control model in both cases. In these instances, the chi-square tests were calculated using the distribution of retreat and nothing reactions to the test and control models. In every case, the chi-square values are very significant. The tests designed to determine the importance of the white tips of the appendages in the behavior of 2 species yielded mixed results. The distributions of reactions shown to the models with the white tips colored were not very different from the distributions shown to the aggressive models with normally colored appendages. In both Calcinus tibicen and Clibonarius tricolor, the reactions shown to the colored appendage models were statistically different from the reactions to the control model. However, in Calcinus tibicen, these were not different from those shown to the normally colored cheliped extension model. Chi-square equals 1.214, p greater than 0.2. Thus it would appear that the white tips of the chelipeds are not visual aggressive stimuli. In C tricolor, the aggressive stimulus value of the ambulatory rays display was significantly decreased by the elimination of the white tips of the ambulatories. The difference in the reactions shown to the 2 test models is significant. Chi-square equals 5.86, p less than 0.02. Thus, the white tips on the ambulatories of C tricolor do act as aggressive stimuli. If the chi-square values for the differences in the test and control sets of reactions are accepted as a measure of the stimulus value, the relative importance to the crabs of these limb positions may be judged. In Calcinus tibicen, the cheliped extension is a stronger stimulus. Chi-squared equals 24.17. Then the ambulatory rays, chi-squared equals 13.04. However, in Clibonarius tricolor, the ambulatory rays is a strong stimulus. Chi-squared equals 23.37. As with C tricolor, the ambulatory rays is a stronger stimulus than the cheliped extension in Clibonarius cubensis and Paguristes grayi. In all the pagurid crabs tested, the cheliped extension was a stronger stimulus than the ambulatory rays. The ambulatory rays in Pagurus bonarensis had the lowest value for any normally colored posture tested. Chi-squared equals 8.69, while the reactions of Pylopagurus operculatus to the cheliped extension model were the strongest shown. Chi-squared equals 24.20. Also of interest is the difference in the number of times that aggressive behavior was shown toward all models by individuals of Calcinus tibicen, Paguristes grayi, and Pagurus bonarensis, as compared to the few shown by Clibonarius tricolor and all other species. In another series of presentations concerned with the analysis of visual stimuli in these hermit crabs, the reactions of individuals to the sight of a hermit crab in its shell was tested. The stimulus in this series was the sight of the crab itself, as a mirror was placed in front of the crab. As in the model presentations, 50 or more specimens were tested individually. After the crab's adjustment to the test container, a small 5.5 by 8.0 centimeter mirror was moved vertically down to a position about 1 centimeter from the crab and then held there for 3 seconds. The crab's reactions were recorded. The reactions shown by all the individuals of each species are listed in the table below. In some species, Caltibicin, Clib tricolor, and Pag miamensis, individuals were tested twice. Once after being a member of a group of conspecific individuals for a number of hours, and once following 3 hours of isolation in individual containers. Pilot tests had indicated a possible difference in the reactions to the test situation depending on the individual's social environment just prior to testing. However, analysis of the data revealed no statistical difference in the reactions shown by the crabs tested after the 2 treatments. Reactions to mirror presentation. A table I am not reading. It can be seen that in some species, the most frequent reaction shown by the crab being tested was retreat from the image of itself. This was true with Calcinus tibicen, Clibinarius tricolor, Pagurus miamensis, P. bonarensis, and Pilopagurus operculatus. Apparently, the sight of a crab of the same size, even though in a neutral position, is sufficient to elicit retreat. The reactions to the sight of a complete crab in its shell appears to be stronger stimulus than the cephalothorax and appendages alone, such as were used in the model presentations. Admittedly, the models on glass rods were moved slowly toward the crab, while the mirror and accompanying reflection were presented all at once by the vertical movement involved in presentation. This method was used to avoid creating the waves that would have been caused by any horizontal movement. However, the retreat reactions shown in the latter case are much more frequent than the retreats shown to the control neutral models in the model presentations. If equality of presentation methods could be assumed, this would indicate that a crab in a shell has a higher stimulus value than a similar crab not in a shell. Individuals of Pagurus marshi tended to not react at all to the presentation of the mirror. In fact, this species' distributions of reactions in the 2 sets of visual test presentations, mirror and control models, are very similar. Perhaps the detritus camouflage on the shell decreases its aggressive stimulus value. Even more likely is the possibility that individuals of this species cannot judge the size of a conspecific individual due to the camouflage, unless it executes an aggressive display. Individuals of Pagurus pygmaeus reacted 84% of the time and did eventually retreat 78% of the time. However, the majority of those retreats were preceded or accompanied by the execution of an aggressive display. Thus, the sight of a conspecific individual evoked an aggressive reaction in P. pygmaeus, but initially a positive rather than a negative one. As described in an earlier section, Clibinarius tricolor gathers in dense aggregations during the day. In order to see if visual stimuli play a role in the formation and/or maintenance of these groups, a series of tests were carried out. The fact that the aggregations are formed for the most part before sunrise made the existence of visual stimuli seem less likely. A large enamel pan was utilized, see figure below. The bottom was covered with sand partitioned into 3 sections with dividers of clear plastic. The plastic dividers were held in place with putty, making the compartments watertight. 15 specimens of Clibonarius tricolor were placed in the right or left compartment, and the individuals to be tested were placed in the center, one at a time. Their position in the pan 5, 10, 15, and 20 minutes later was noted. The test side was alternated frequently. Although this experimental method would not eliminate any possible auditory signals, it does eliminate the possibility of chemical cues. All tests were carried out in the morning and early afternoon. 35 individuals were tested, 2 of which did not move during the test period. The results are shown in the table below. As can be seen, no orientation was shown, either in the total time spent in the two half of the middle section, represented by the number of times a crab was observed in one half or the other at specified times, or in the initial direction of movement. Table 7. Reactions to static models by Diogenid crabs. A table I am not reading. Table 8. Reactions to static models by Paguridae crabs. Another table I am not reading.